Hello students, this is Mr. Allen. Today we're going to look at the ratio and root test. This will be the last test that we look at before we move on to the second half of this chapter, which will be on Taylor series and Maclaurin series. So just to let you know, our objectives today are to use the ratio test to determine if a series is convergent or divergent. Use something called the root test to do the same thing. And finally, I'm going to spend a little bit of time just reviewing some of the different tests for convergence. So first, let's look at the ratio test. So this is, if you're someone that is keeping track at home, this particular test, the slide here is an important one. This is called the ratio test, and ratio means fraction. And basically, here's what you need to know. As long as the series is non-zero terms, then the series will converge and converge absolutely if the absolute value of the a sub n plus term divided by the a sub n term, as we take that limit as n goes to infinity, if it's less than 1, then it will converge absolutely. If it's greater than 1, or if it's equal to infinity, then it will diverge. And if it is equal to 1, then the test is inconclusive and you cannot use it to conclude if it converges or diverges. So let's look at an example of using the ratio test. So here we have an infinite series, 2 to the n over n factorial. We want to figure out if it converges or diverges. So what we're going to do is we're going to first, lost control here, sorry. First thing we want to do is know that the a sub n term is simply this 2 to the n over n factorial. And therefore, we can write our limit as the absolute value of a sub n plus 1 over a sub n is simply going to be the n plus 1 term. So if this is a sub n, then a sub n plus 1 just means that it's going to, be 2 to the n plus 1. That's a plus, sorry, over n plus 1 factorial. So that's what you see here. So here's the n plus 1 term divided by the a sub n term. And we can quickly multiply that, or change that division to multiplication by multiplying by the reciprocal. And here we're going to see lots of cancellations. The 2 to the n's are going to cancel all but one of the 2 to the n plus 1s. And the n factorial will cancel everything but the n plus 1 term of that. So we end up with 2 over the n plus 1 as n goes to infinity. Clearly that is equal to 0, which is less than 1. Therefore, we can conclude that this series converges. This series is going to converge because, remember, based on our last slide, if we have that this limit is less than 1, then it will converge. That's the ratio test. Let's look at another example. This one I'm actually going to work out by hand. So we want to figure out if this one converges or diverges. You'll notice that it looks very similar to the last one. The last one converged. Let's see how this one shakes out. All right, so the first thing we establish is that the a sub n term is n to the n over n factorial. Therefore, the a sub n plus 1 is going to be n plus 1 to the n plus 1 power all over n plus 1 factorial. So that's going to give us our two terms that we're going to need. So now what we want to do is do the limit as n goes to infinity of the absolute value of these two guys. Now, guys, everything here, we're talking about 0, right? So everything's going to be non-negative. So we don't need the absolute value here. I'm going to go ahead and write it anyways, but it's not really necessary. Remember, we're wanting to do the a sub n plus 1 over the a sub n term. So in this case, it's going to be the limit as n goes to infinity of, so I got to do the n plus 1 part first. And we need to divide that by n plus 1 factorial. And I'm going to go ahead, instead of dividing, I'm actually going to go ahead and multiply by the reciprocal. So the reciprocal of the a sub n term is going to be n factorial over n to the n. Now, not a whole lot cancels here initially. So we have this n plus 1 factorial, which is the same thing as n plus 1 times n factorial. So the n factorials will cancel. So that's going to give us the limit as n goes to infinity of 1 over n plus 1 times, and now I'm going to do all the powers of n over here, so that's going to give us n plus 1 to the n plus 1 over, that's a plus there, over the n to the n. Now, it doesn't look like much cancels here, but you'll notice carefully if we look, if I were to put parentheses around this n plus 1, that's going to cancel one of those factors in that numerator. So that's going to make our limit here now be n going to infinity of n plus 1 to the n, and then that cancels the denominator. So essentially, here's what's just happened. We've canceled that plus 1 there, and we've canceled that n plus 1 there. So that leaves us in the denominator of n to the n. Well, you'll notice everything here is written to the nth power. So we got the limit as n goes to infinity of n plus 1 over n to the nth, which can be further written as the limit as n goes to infinity. And I can break this quotient into the sum of two fractions, and those two fractions would be 1 plus 1 over n to the n. And at this point here, I hope you're getting a little bit excited, because that should look very, well, maybe not very familiar. Hopefully it looks familiar to you. This, by definition, is E. And I should note that E is greater than 1. And since E is greater than 1, we can conclude ... that this series diverges. And the series diverges by the, and we'll call this the ratio test. Okay, so I did that one all the way through. I'm sorry that my handwriting isn't better, but hopefully you can follow that one. I kind of want to do some of these by hand, because I just want you guys to feel like I'm just not doing the work. So there you go. All right, so now let's look at, here's the second most important slide in this presentation, and that is the root test. And here we're basically, instead of the ratio test, you're using a ratio, a fraction. Here, the root test, we're doing a root. So if we have a series, it will converge, and converge absolutely if the nth root of the absolute value of a sub n is less than 1. So this is kind of similar to the last one. So if it's less than 1, it would converge. It will diverge if it's greater than 1, or if it goes to infinity. Again, that kind of makes sense. And similarly to the last one, if it's equal to 1, it is inconclusive. So this is very similar to what we saw on the ratio test. So let's go ahead and look at an example of this one. It says determine if the convergence or divergence of this series. We got e to the 2 to the n over n to the n. You'll notice that they both have a power of n in them. Now notice the top one is 2 to the n, but that's okay. So we can apply the root test as follows. We need to do the limit as n goes to infinity of the nth root of the absolute value of a sub n. Everything here is positive, so I don't have to worry about absolute value. So I'm just going to plug in the a sub n term of the radical. I'm doing the nth root of it, and guess what's going to happen then? So since we're doing the nth root, we're basically doing the division of the exponents by a factor of n. So that's going to give us the limit of e squared over n. And that, of course, is going to go to 0, which is less than 1. Therefore, it converges, and it converges absolutely. And that's by the root test. This is called the root test. Okay, so now we've seen all the tests. We've done the geometric series test, p-series test, integral test, both of the comparison tests, ratio test, now root test. I think I mentioned most of them. we're going to see them again. So the rest of this presentation, I'm just going to review some things with all of these different tests. You probably will want this PowerPoint because it's got some good concise notes for all of the tests in one document. It says guidelines for testing a series convergence or divergence. Number one, just look at the nth term. If it doesn't go to 0, you know that it diverges. So instead of wasting your time, you could check that first. That's a quick thing to do. Number two, is it a special type? Does it look like a geometric, a p-series, or I should have mentioned, I forgot to mention telescoping and alternating series. Those are two special cases. The alternating is pretty simple. This guy here, this telescoping, that's the one that gets students. They forget about that one. And it's hard to see if you're not careful. Can the integral and the root test or the ratio test be applied? Can a series be compared favorably to one of those special types? So kind of the last place you may want to go is the comparison tests. First thing you want to do is try to get rid of it using the divergence test. So those are just guidelines. You don't have to listen to these or follow these. This is just some suggestions. Now what I'm going to do is go through, I think I got 7 examples here. I'm actually not going to work them out. I'm just going to talk through them and explain some strategies. So here are the 7. If you want to write them down, you can. I'm going to try to include them in the following slides. I've got my text already written out so that you don't feel like you have to write all these out. So let's go ahead and look at the first one. So, and I've kind of got it cut off here a little bit. So A here. So if we look at this series, this is where you're just going to use that divergence test, the nth term test. So it's going to turn out that the limit of a sub n is going to go to infinity. Therefore, this series has to diverge because at the end, as n is large, the terms are 1/3, and you're adding 1/3 forever, which is going to go to infinity divergence. Don't do anything else. You're good. Second one, that looks kind of like a geometric series, and it is. And it turns out in this geometric series that r here is pi over 6. Pi over 6 is less than 1. And so you can conclude it converges. All right, number 3, this one we're going to use the integral test. You can't use the first case, the nth term test. It's not geometric, so we're just going to use the integral test, and it integrates pretty easily using u sub. You would let u equal negative x squared, and you will be able to conclude that this one converges. What's that last one look like? Well, I hope you remember it looks like the generalized harmonic series. That's exactly what this one is. So we can use the comparison test. We can compare this to the p series with 1. So this is going to, with p equaling 1, so this one's going to diverge. All right, the next one. Here we have an alternating series. So the only thing we need to do basically is we need to make sure that a sub n plus 1 is less than a sub n. And we will be able to figure out that this one does converge. Looking at F, that's going to be the ratio test. So we got factorials. Anytime you got factorial, I shouldn't say anytime, most of the time you've got factorial, ratio test is one of the best ways to do it because the factorials will cancel. And in this case, you will find that it diverges. And last but not least, what's one that we have not mentioned? Well, it's the last one we talked about today, which is the nth root test. So all we're going to do here is we got this thing raised to a power. So all I would do is the nth root of it, take the limit as n goes to infinity. Everything's going to cancel out lovely. You're going to get 1/2. It's less than 1. Therefore, this is going to converge. Now, I just went through those very quickly. You might want to rewatch those or think about those a little bit more. When it comes to actually doing these, remember, you kind of have to figure out which way to go. So this requires some practice. Now, the last few slides of this presentation include kind of a summary of the different tests, like the nth term test, the geometric series, telescoping series, p-series, alternating series, integral, root, ratio, direct comparison, and limit comparison tests. So that's where we're at, and I think we will stop it there. Have a good day.